In this video we present our work, Panoptic NeRF, 3D to 2D label transfer for Panoptic urban scene segmentation. Like many deep learning-enabled computer vision tasks, allowing machines to understand the world through semantic information requires a massive amount of high-quality annotated labels. Manual annotation of pixel-accurate segmentation masks is highly expensive and time-consuming. We advocate a more efficient annotation approach by labeling in the 3D space using coarse bounding primitives. It allows for reducing the average annotation time of a single frame from 1.5 hours to 0.75 minutes. However, how can we transfer 3D labels to per pixel dense 2D annotations? In this work, we introduce Panoptic NeRF, a novel label transfer method built on neural radiance field, which infers in 3D space to render dense 2D semantic and instance labels. This task is non-trivial and faces several challenges. Firstly, NeRF fails to recover good geometry when only guided by the photometric loss on sparse views. Erroneous geometry leads to inaccurate object boundaries when only 3D bounding primitives are available. Furthermore, the 3D label provided by the bounding primitives is ambiguous at intersections of bounding primitives. Semantic NeRF aims for label denoising given noisy 2D predictions. Yet label denoising is hard in our setting given poor geometry and noisy 2D predictions of pre-trained 2D models instead of synthetic noisy 2D labels. Meanwhile, when leveraging both 3D bounding primitives and noisy 2D predictions, existing 3D to 2D label transfer methods cannot jointly optimize geometry and semantic estimations. To address these challenges, our proposed method leads to improved geometric reconstruction guided by semantic information and resolves label ambiguity by unifying 3D and 2D semantic information. Moreover, it allows for rendering panoptic labels using 3D bounding primitives. To jointly optimize geometry and semantics, we propose dual semantic fields. Firstly, the fixed semantic field is determined by the 3D bounding primitives. By querying whether the 3D point is enclosed by the bounding primitives, it outputs a corresponding fixed one-hot semantic categorical distribution. Then, via volume rendering, the fixed semantic map can be obtained. Secondly, we design the learned semantic field. It generates the learned semantic map by optimizing the MLPs. To improve the underlying geometry, we leverage noisy 2D semantic predictions as pseudo-ground truth and apply cross-entropy loss on the fixed semantic map. To illustrate why it boosts density prediction, consider a ray marching through the image. If its corresponding pseudo-semantic label is correct, it increases the volume density of 3D points inside the correct bounding primitive and suppresses the density of others. Otherwise, it will cast no or little influence in backpropagation. Moreover, to resolve the label ambiguity at the overlapping region of bounding primitives, we introduce masked cross-entropy loss on the learned semantic map. Though pre-trained segmentation result is noisy, we observe that it usually performs well on the boundaries, so it provides the prior in the intersection region of bounding primitives. We now show label transfer results on video sequences. We firstly compare our method to baselines on the semantic label transfer task. Our method outperforms all baselines and produces multi-view consistent labels. Next, we compare our method to the CRF on the Panoptic label transfer task. The results indicate that our method is superior to the CRF approach. Then, from the novel viewpoints, we show the rendered images and label synthesis results. Finally, we show rendered depth maps for qualitative comparison of geometric reconstruction. Using the semantically guided geometry optimization, our method yields more accurate depth maps. Thank you for your attention.